This is going to be one of the hardest problem we are solving on this channel. And this is from School of Science and Maths journal proposed by Sharma India. Okay, so you can see this integral from 1 to infinity, sum of fractional part over here, sk by k to the power 8 by x to the power 9. So first of all, let me just introduce you to fractional part, sk, zeta function that are over here. Okay, so first of all, fraction part for n is just n minus floor function of n. That means for 2.5 it's just 2.5 minus 2, that's 2. For 3.1 it's 3.1 minus 3, that's 3. Sorry. That's 0.5. And for 3.1 it's 3.1 minus 3, that's 0.1. But for negative numbers it's negative 1.1 minus negative 2, because floor of minus upper bound is minus 2, so that's 0.9. I guess you weren't expecting that, eh? And from 4.2 floor is 0.2. So that's about floor function. And next we go to what sk is. Now the sk is the kth harmonic number. Yeah, Sn is nth harmonic number. So sk will be 1 plus 1 by 2 plus 1 by 3 up to k. So if we are asked, let's say as 3, it will be 1 plus 1 by 2 plus 1 by 3. So that's 6 over here. And 6 plus 3 plus 2, that's 6 over 9, 11 by 6. So this is third harmonic number, and so that's what sk is. And next, what's Riemann zeta function? Riemann zeta function is just the sum of inverses, and inverses raised to some power. Okay, so Riemann zeta of n is 1 by n plus so 1 by 1 to the power n plus 1 by 2 to the power n plus 1 by 3 to the power n plus 1 by 4 to the power n till infinity. So this is what Riemann zeta function is. And you might have probably known some popular values like Riemann zeta function of 2, that 1 by 1 square plus 1 by 2 square plus 1 by 3 square. This is equals to pi square by 6. And similarly, Riemann zeta of 4 equals to pi to the power 4 by 90. You should have heard some values. And Riemann zeta function of 1 does not converge. So these are the examples of Riemann zeta function. Now let's move on to our problem integral. Okay. So our integral is like this. Integral from 1 to infinity. And now for the summation world is of k. So for this, x to the power 9 will be a constant. So we can take that into the summation as a constant, since the sum world is all made of k, so it is of k. So that's a constant over there. And sk by k to the power 8 dx. Now we're interested in the sum in integral sign, since our integral is linear. And then we will have summation from k equals to 1 to infinity, integral from 1 to infinity, fractional part of k of x as k by x to the power 9 times k of 8 dx. Okay, now we'll try to bring the constant like sk and k to the power 8 out of integral sign, since it is x world and these k terms will be just constants. So we'll bring them out of the integral. Summation from k equals to 1 to infinity as k by k to the power 8 from 1 to infinity, fractional part of k of x over x to the power 9 dx. Now we'll first deal with this integral and then later on come back to it and make the summation. Okay, so now our measure is just to find the integral. So our integral is integral from 1 to infinity, fractional part of k of x over x to the power 9 dx. Now we would like just one variable over the fractional part, so we can make y equals to kx substitution, and this gives dy equals to k dx. Okay, and change of limits will be for x equals to 1, y equals to k, for x equals to infinity, y equals to infinity. And here fractional part of y, and x is y by k to the power 9, and dx is dy by k. So now k to the power 9 and k, one of them cancel out and the other will go to numerator. So we'll have k to the power 8 from k to infinity, fractional part of y over y to the power 9 dy. Now, how will we deal with this integral involving fractional part? We will use some pretty good ideas, pretty good concepts. So we will change the integral into sum like this. In the sum from n equals to k to infinity, and integral from n to n plus 1. So by this way, when n equals to k, we have integral from k to k plus 1. When n equals to k plus 1, we have from k plus 1 to k plus 2, k plus 2 to k plus 3, k plus 3 to k plus 4, and so on till infinity. So we have all the integrals that are here. And so this simplifies how we deal with fractional part of y. This is actually y minus floor of y. So y minus floor of y is just n over here. Yeah, and y to the power n dy. So k to the power 8 integral for sum from n equals to k to infinity, and this will be 1 by y to the power 8, that the integral is minus 8 y to the power 8. Sorry, no. Let me do all the process. Sorry, no, not. This happens, it's often lags. Now this will be y minus n by y to the power 9 dy. Okay, by 9 dy. Now let me go with all the details. Let me not skip them. From n equals to k to infinity. So this will be integral from n to n plus 1. We will have y to the power minus 8 minus n times y to the power minus 9 dy. Okay, and then the next step will be k to the power 8 sum from n equals to k to infinity. This integral over here will be y to the power minus 7 by minus 7, minus n times y to the power minus 8 by minus 8 from n to n plus 1. Okay, so after this we'll just substitute the limits of integral k to the power 8, let me write it properly, k to the power 8 summation from n equals to k to infinity. And now when we substitute this, we have 1 by minus 7 n plus 1 to the power 7, and for this we have plus n by n plus 1 to the power 8, and we will have plus, you are here, minus plus, and we will have 1 by 7 n to the power 7, and over here we will have again minus. Now since it was plus, now it will get minus, and n, sorry, yeah, so this will get n by, okay, I just forgot the 8 over here, n by 8 times n to the power 8. Okay, so that's what we get over here, and now we'll just try to evaluate the sums. K to the power 8 sum from n equals to k to infinity. And we can just see that we here have a telescoping sum over here. If we just take 1 by 7 common over here, we will have n to the power 7 from here, and from here we will have 1 by n plus 1 to the power 7. So that's a telescoping sum that we have found. Again, we can also change this n into n plus 1 minus 1 by 8 n plus 1 to the power 8. That can give rise to another telescopic sum, I guess. 8 n to the power 8. So we can cancel that out, in fact. This will be 1 by 8 n to the power 7. Yeah. Now we have k to the power 8. This will be 1 by k to the power 7 minus 1 by k plus 1 to the power 7. And again, plus 1 by k plus 1 to the power 7 minus 1 by k plus 2 to the power 7. And again, plus 1 by k plus 2 to the power 7. So, except the first terms, other are going to cancel out. So, we will have here 1 by 7 and then times 1 by k to the power 7. And let's evaluate the other integrals. N equals to k to infinity. Now this one is going to be 1 by 8 n plus 1 to the power 7 minus 1 by 8 n plus 1 to the power 8 minus 1 by 8 n to the power 7. Okay, so it's cool. That's cool. Now the next step. Again, we see that here's a telescoping sum. Yeah. So k to the power 8, 1 by 7 k to the power 7 plus, that's really bad. Why does it happen? 8 n plus 1 to the power 7. Now from this telescoping sum, what we have as remaining as what we have as our answer is 1 by 8 k to the power 7. Yeah. No, how to exactly do this? Okay. Now when we have n equals to k, so first term will be this, and the others will just cancel out. Only the first term remains, which is this one. And now we need to deal with this one. And negative of summation from n equals to k to infinity, 1 by n plus 1 to the power 8. Okay. We have made up quite a lot of progress. And now we have k to the power 8, and this will be 1 by 56 k to the power 7, and here this will be, how can you, this is from sum from k plus 1 to infinity. So in fact you can write it as zeta function of 8 minus sum from n equals to 1 to k, 1 by n plus 1 to the power 8. I guess you can do that. Yeah. We can write this as sum from n equals to 1. Wait. No, we don't need n plus 1 over here. Okay, because this starts from k plus 1 when n equals to k. So from k plus 1 till infinity it goes. So here we only need n because we want it to up to be up to k only. Yeah. So what we have done here is this zeta function of 8 is from 1 to infinity. This one was from k plus 1 to infinity. So we subtracted from 1 to infinity minus 1 to k, so that it gives k plus 1 to infinity. And you know that zeta of 8, I guess you have understood this, because zeta of 8 is just 1 plus 1 by 2, 1 plus 2 by 8 plus 1 by 3 by 8, 3 by 8 plus 1 by 4 by 8 till infinity. And this sum subtracts from 1 plus 1 by 2 plus 2 to the power 8, 3 to the power 8 up to k. So it subtracts up to k, and when we subtract this from this, we will get this sum, which was from k plus 1 to infinity here. I hope you got it now. Now after we have this, we are pretty close. Now this will be yeah, this is what the sum looks like. Now we will substitute it back in the original expression. Original expression was integral, summation from k equals 1 to infinity as k by k to the power 8, and the integral then. So this will be summation from k equals to 1 to infinity as k by k to the power 8, and then this integral is k to the power 8 times 1 by 56 k to the power 7 minus zeta of 8 minus sum from n equals to 1 to what's this k, okay, k 1 by n to the power 8. Okay, now this cancels out. This nicely cancels out. The one who created problem should have looked up on this, should have made that to cancel out. So now it's from k equals to 1 to infinity. We can now distribute this sum as k by 56 k to the power 7 minus as k by gamma of zeta of 8 and sum from n equals to 1 to k 1 by n to the power 8. Now, and I distributed this because we can evaluate this from classical Euler formula. Yeah. So how we can evaluate as k by k to the power 7 is, we have a classical Euler formula, okay, which goes like this. In the formula, okay, so this one is typically known as zeta and adds of 7. So this the value when we take 156 common and out of this sum from 1 to infinity as k by k to the power 7 is generally written like this, and for such zeta adds of q, where q is this number, we have the formula that it's equals to summation from n equals to 1 to infinity at n by n to the power q. So this is equals to this, and the formula for this one is 1 plus q by 2 zeta of q plus 1, and generally we know such values, zeta of q plus 1 and minus 1 by 2 sum from k equals to 1 to q minus 2. Yeah, it's quite complicated though. And summation from zeta of k plus 1 and then zeta of q minus k. So this is the formula, and since we know zeta of all the even numbers, and for odd numbers they are just constant, as they are just taken as constants, so we can find the value of the zeta adds of 7. Okay, for now we will just denote it as this, and we will assume that its value can be found through Wolfram alpha or anything like that. So that's it. Now we have already solved for this one. We assume that. Later on I will also tell you what will be the value of zeta adds of 7 by evaluating with this formula. I will do that later on. Okay, for now this is just 1 by 56, and then zeta adds of 7 and minus. Now we need to deal with this summation from k equals to 1 to infinity as k as zeta of 8 minus summation from n equals to 1 to k 1 by n to the power 8. So now we need to deal with this summation. So now again, let's just focus on sum rather than anything else. So I just want to change the variable st zeta of 8 minus summation from n equals to 1 to t 1 by n to the power 8. So let this sum be s of t. Let's write subscript st. So sum do this. Now in integration, when we have product of two expressions, we are likely to use integration by parts. Yeah, in summation also we have summation by parts, which is also known as abel summation formula. We have in summation abel's summation formula, which goes like this. It is quite similar to that of integration though. summation from t equals to 1 to infinity. Summation from t equals to 1 to infinity at bt is equals to limit n goes to infinity, and then we will have over here b of n plus 1, and then summation from t equals to 1 to n a of t. Okay, it's just like integration of a f of x, g of x, dx was f of x times integral of g of x, and then we evaluate it from in the limits are in the limits of integration, and then we have a negative sign over here, and then we have summation from k equals to 1 to infinity. Okay, and this one, let me say rather than k, we can yeah, we can do anything, of course. Here's just n, and here, yeah, let me do k. If there is variable mismatch of later on, I will just adjust that. And here we will have the derivative of b. Okay, so that's b of k plus 1 minus b of k, and then here integral of a, so that would be summation from t equals to 1 to k, and then over here that is a t, yeah, a t. So it's just similar to integration formula, where this one is u, this one is b. U integral of b minus integral of d u, and then integral of b. Yeah, it's similar. Now we will first try to find this expression, and then we will find this expression. Okay, so now for this we will take this one as a of t, okay, and this one as b of t. Yeah, now we'll just try that. It's quite complicated, though. It looks complicated. So first let's just evaluate this part, the first part. So limit n tends to infinity, n tends to infinity, our b of n plus 1 will be okay. No, I guess it would be better if we just take this part as a, I guess. If we take this part as a of t, that will be better for us, is it? Shall we do that? This will become no. Let's make it as it is. So b of n plus 1, so that's gamma of 8, and then minus summation from n equals to 1. So since this was b of t, and now we need to find b of n plus 1, we'll replace here this t by n plus 1. Okay, so n plus 1 and 1 by n to the power 8. Okay, so this is b of n, and this thing is summation from t equals to 1 to n, and here a t. So a t is just s of t. Okay, so this is our front part of the sum. Yeah, and now you will notice that I have taken this one. It goes from n equals to 1 to t, but I guess here we should have taken some other variables such as s, so that here would be something like s plus 1. Yeah, and then that would be easier. But at least these two variables are different. The variables that starts the counting and the endings are different. Yeah, we know that by ourselves, and this one is equals to infinity. N plus 1 goes to infinity since n goes to infinity. So this sum over here is also zeta of 8. So these two are equal, so they cancel out nicely, and that's 0 times some other things, whatever that is. So it's 0. So the front part is 0. We know that now. Now we are trying to express the second part. Let me just cancel. Let me just delete it for some time, since you know this is 0. Okay, and now for this thing. Yeah. And now for that one, we have summation from k equals to 1 to infinity. And now b of k plus 1. B of k plus 1 will be zeta of 8 minus summation from n equals to 1 to k plus 1. Yeah, that would be zeta of 8 minus summation from n equals to 1 to k plus 1, 1 by n to the power 8. And b of k needs to be subtracted, that is zeta of 8 plus summation from n equals to 1 to k 1 by n to the power 8. So this will cancel out, and the remaining will be just 1 by k plus 1 to the power 8 and negative sign. Yeah, from these two also one of the last term from this sum remains. So we'll just write that one because it's getting messier over here. So we'll just write that one out. Yeah, it will just be negative of 1 by k plus 1 to the power 8. Okay, and also we can just remember these two are, both of them are negative sign, and we just have product over here, so we can just cancel those signs. So you can also do that. You can cancel those signs, these two, because they get into plus. They send into plus. Minus minus is just plus. You can do that. Now it looks quite simpler. And here we have summation from t equals to 1 to k a of t. Yeah, so we are summing from t equals to 1 to k, a of t will be h of t. Okay, now we have a formula for such summations. When we are summing the nth harmonic number up to k, so sum of harmonic number, we have a formula for that. If we are summing till k, and you can also prove that result just from induction. 1 to infinity, 1 by k plus 1 to the power 8. So this will be t plus 1. Yeah, t plus 1, and then over here h of t plus 1, and then minus 1, h of t plus 1, and then minus 1. You can prove this result from induction as well. Yeah, I have tried proving this and I was successful. But since it's from k, so since it is up to k, we need to write here k. It's in the form of k and not t. I'm sorry for that. It's k plus 1, h of k plus 1 minus 1. Yeah, so we get this sum from 1 to k in terms of k plus 1 harmonic number. Subtract 1 from the k plus 1 harmonic number and just multiply that by k plus 1. Okay, so yeah, from k plus 1. And now we have a good cancellation over here. Now we have a good cancellation over there. Yeah, sorry. Now we have a good cancellation over there. So we have summation from k equals to 1 to infinity, 1 by k plus 1 to the power 7, h of k plus 1 minus 1. Yeah. And now we can make a slight change over here. Since if it was, this runs from 2 to infinity, yeah. If it went from 1 to infinity, we could have written it in terms of zeta function. But here we can also make slight changes. We can express this h of k plus 1 as this can be written as h of k h of k, let's try it like this: h of k plus 1 by k plus 1 to the power 7 and minus 1 by k plus 1 to the power 7. Okay, both of these run from 2 to infinity, and now the first term for both of this series is same. The first term for this series is also h of 1 by 1 to the power 7 and watts of 1 is 1, so 1 by 1 and here also 1. So we can make something like, we can make a change like this. We can make a change that uh, if we run it from k equals to 1 to infinity, and if we just make it as k by k to the power 7, yeah, and then we need to subtract the first term, which is just 1 over here, and we can do a similar thing over here. Extremely sorry. Yeah, that's k by k to the power 7 minus 1, and then negative of 1 by k to the power 7 minus 1. We can do this, and these ones cancel out. Why is this happening? I'm extremely sorry. So we know that those ones cancel out, and this will be minus 1 by k to the power 7. So now again we know that this is just zeta h of 7, and the other is just zeta of 7. So we get this nice sum. We get this nice sum for this summation thing. Okay, so now this summation came out as the following: zeta h of 7 minus zeta of 7, and this one was okay. Now we'll just substitute that over here. 1 by 56 zeta h of 7. Yeah, we will substitute that over there. 1 by 56 zeta h of 7 minus this thing, zeta h of 7 minus zeta of 7. So it comes out as zeta h of 7 by 56. I don't know. Start normally. Just want this to complete. Yeah, just want this to complete. You can just do it slowly. Because if it goes on like this, it will just clear all the data, and I don't want that. So 1 by 56 zeta h of 7, and we will have here minus 1. Okay, if we take that out common, and over here we'll have zeta of 7. Okay, so yeah, is it, do we really have this over here? What we had 1 by 56 and minus this sum over here, and we evaluated that sum, but over here I guess I'm missing some coefficients over here. Let me go back. Okay, if we go back over here, yeah, over here we had 8, and yeah, we had that 1 by 8 over here as well. This one looks messier now, but here when we, what did we do here? Here we had 8 1 by n plus 1 to the power 7. We had that, and minus of 1 by 8 and yeah. And now here we had, what do we had? What do we have? Okay, yes, this is, and now this one is there, and here, and these two were telescoping sum, and here, yeah, and this one came down over here, and I just missed the 1 by 8 over here. I now realize that. I now realize this. So 1 by 8, this passes down, 1 by 8, this passes down, 1 by 8, this passes down, 1 by 8, 1 by 8, okay, so this 1 by 8, is it here actually, or somewhere around 1 by 8, it's here actually, it's really there. It's just bad that I forgot it. So it was 1 by 8 over here. Mhm. Yeah, it's over here as well, 1 by 8, because this was converted, and so it gets out here 1 by 8, and but then when we multiply, it gets here 1 by 8, and it gets out from over here 1 by 8, and it gets out over here 1 by 8. Okay, so it's out now, and we just evaluated the sum. Okay, and then that should have been here, that should have been out of the sum. Yeah, just follow that. What was that? Doesn't matter anyway. Okay, they didn't write it in the h of k plus 1 by k plus, oh sorry, it was h of k, so it's saying that h of k by k to the power 7. Okay, and this over here, h of 7 minus gamma of 7. Okay. And now let's continue. So this here we have 1 by 8, and yeah, and now I have minus 1 by 8 over here. Okay, and over here I have 1 by 8. So now this will be we have here minus 7. Yeah, we have 1 by 56 minus 7 by 56, so that's minus 6 by 56, and the minus 6 by 56 is just minus 3 by 28. Okay, so minus 3 by 28, gamma adds of 7, and plus gamma 7 by 8. Okay, now from the classical Euler formula that I told you earlier, we can find the value of gamma adds of 7. Okay, we can find the value of gamma adds of 7, and that comes out to be something like this. That comes out to be pi to the power 8 by 4200, and minus gamma 3, zeta 5, and zeta 7 by 8. So now you might notice the 3 by 28 coefficient over zeta 3, zeta 5, yeah, which you have already got. Okay, and now we are nearly at the end of the video. We can just multiply that. Yeah, I can do it in my calculator, in my phone. So we have 3 by 28 into 4200, 3 by 24, so that comes out to be negative 1 over 39200 by pi to the power 8, and this comes out to be plus 3 by 28, zeta 3, zeta 5, and this is zeta 7 over 8. I guess we haven't messed up with anything. Zeta 7 over 8 plus 3 by 28, zeta 3, zeta 5, minus pi by 8 by 39200. So we are done. We have finally solved this hardcore problem from a problem solving journal. I guess you have enjoyed the video and we have understood well all the ideas. I went detailedly from all the ideas, and I hope you have understood them. And yeah, so I guess you now feel happy for solving a journal problem. And this was it. Thanks for watching. Looking forward to seeing you in the next video. Thank you.